All right, folks, it's time to get serious about this IoT business. I know, we've all seen the silly connected cactuses and Internet of Cat Toys nonsense. And sure, it's all fun and games, until your smart bathroom scale locks you out of your intelligent beer cooler. But now, IoT has some real work to do, industrial work. That's right. IoT is growing up, getting a job, and actually doing something useful for a change. Welcome to Industrial Internet of Things, or IIoT. Hi, I'm Amelia Dalton, host of Chalk Talk. In today's episode, we're talking with Dan Isaacs from Xilinx about enabling the Industrial Internet of Things, which, it turns out, isn't silly at all. Before we get started, go ahead and click that link. There you can find out more information about IIoT solutions from Xilinx. Hi, Dan. Thank you so much for joining me today.
Yes, and thank you, Amelia.
All right, Dan, before we jump into today's discussion, how exactly is IIoT different than regular old IoT?
That's a great question. Really, if you think about it, the Internet of Things is looking at both a consumer perspective and an industrial perspective. The consumer, we're talking about your smartwatch, talking to your refrigerator, letting you know that you've got to go and buy more eggs. And white box applications. When we talk about the IIoT, the industrial Internet of Things, we're talking about the areas like smart factories, smart manufacturing, smart energy, smart cities. So we're out of that consumer realm and really into the industrial areas. And as you can see, really the value from the Internet of Things is coming from the data itself. And in fact, this is showing a survey from Accenture. You could see that we're really at the very cusp of the industrial Internet of Things and being able to recognize that true value. GE has a story where they call it the 1%. With 1% savings, they can offset the cost of what it takes to actually be able to run their systems. And some of the examples in terms of whether it's aeronautics, whether it's industrial, oil and gas, and transportation, those same type of savings can definitely be recognized within smart factories, industrial manufacturing, these types of applications, again, where we focus on industrial IoT.
Okay, so Dan, IIoT seems like quite a broad category. What areas are you guys focusing on?
In terms of smart energy, we look at it in terms of the smart grid, renewable energy sources. How does that play back in terms of the grid and not bringing that down? Power conversion, obviously very key there. Management of that. Think of it as the generation, the distribution, and the consumption. And we play in all of those areas. And then within smart cities, as I said, infrastructure, communications infrastructure, very key. Aggregating a lot of the sensor data and being able to do analytics on that, as well as in transportation, even within the medical area, many different areas, whether it's in the diagnostics equipment, whether it's managing of that data, handling, analyzing that data. And obviously, with all of these types of areas across this, security plays a very key role, and platforms being designed from the ground up to address that.
Okay, Dan, so what are some of the trends that you're seeing in this space?
Within the industrial IoT, we've really seen the growth of this being driven by the low-cost, widespread proliferation of sensors and the fact that cost of very high-performance computing dropping significantly, and the accessibility to that, again, with the cloud in these types of areas. And then having the platforms that are flexible to be able to accommodate themselves to the different types of requirements that these systems have and still maintain that connectivity and provide that security that's absolutely required.
All right, Dan, tell me a little bit about Xilinx's platforms in this space.
Xilinx, as I said, they've been very well established within industrial type applications, and the differentiating advantages that our platforms provide are very well aligned to the trends that are driving the industrial Internet of Things. And that's the ability to accommodate a variety of different types of sensors and to be able to fuse that information, perform the analytics, and to do that in real time with the configurability of the platforms from an I/O, doing any-to-any connectivity, and being able to provide precision control. And precision, we're not talking just about in terms of accuracy or precision for the processing, we're also talking about precision in terms of the communication and then the time stamping. And with the new evolving standard of the time-sensitive network extension to Ethernet, the TSN, you look at it precision in terms of not just in terms of command control, but also in terms of the communication, the connectivity. And again, having the platforms to be able to, once you develop the system or you develop your software architecture, can you reuse that? So you don't have to start from ground zero for every different application. And being able to take that IP, take the different blocks you have in a very modular way and quickly build your development back up and bring products to market. And another area, obviously, would be in terms of that security. And with our platforms, another big differentiating advantage, we really are the only single-chip programmable devices that provide both multi-layered security and multi-level safety from a functional safety and very key safety integrity levels, the SIL levels, within a single platform.
Okay, Dan, so you mentioned programmable SoCs. What do programmable SoCs bring to the party here?
Yeah, that's a great question, Amelia. If you look at it, you can see our programmable SoC, we really innovated this concept with our Zynq SoC devices. And what it does is it takes a complete processing system. This is our Zynq 7000 that you're seeing. This is based on a dual Cortex A9, but it gives you the complete peripherals, everything you would see in a discrete processor, memory, peripherals, even coprocessors, but it marries it very closely to the programmable logic. If you look at the processor subsystem, and then you can see safety and security elements, and then you can see the FPGA. If you think about it, the processing system, there's over 3,000 interconnect between that processing system and the programmable logic, the FPGA. And you can run your standard operating systems, do everything you would do in a discrete processor. But now with the FPGA, you can have full programmability. You can take algorithms that you would be running on the processor. You can accelerate those. Say you needed additional peripherals. You can implement those peripherals in the programmable logic. So it really does give you a truly customizable processing platform. And some of the features there you see with the sensor fusion, being able to accommodate, because of the configurable I/O again, a variety of different types of sensors and industrial Ethernet protocols. That's where that any-to-any you're looking at comes into play, and being able to support a variety of different types of protocols and standards. And then always being able to then be complementing any of the real-time command control, even the analytics being run in the FPGA, being able to complement those with the cloud connectivity where it's not as time critical.
All right, Dan, so you said you're in production with the Zynq SoC, but what if I want higher performance and some more features? What do you got down the line a bit?
Yeah, that's a great question. The Zynq 7000 was the first device, and what we did was, after talking to quite a few customers, we were looking at what would be the next big focused area.
Okay.
And we heard continuously that customers wanted to be able to run virtual systems, virtual OSs. And what we did as a result of that was we went with the 64-bit Cortex A53 processing system. So our latest device is the Zynq UltraScale Plus programmable SoC, and that actually has a quad 64-bit A53 processing system. It also has quite a bit of other dedicated processor functions within it. So we really looked at this as a platform that would give our customers and developers the right engines for the right tasks. And when I talk about the right engines, I'm talking about being able to have both application processing and real-time processing. And this is the only device that has both application processing with the Quad A53s and dedicated real-time processing with R5s. And that gives the ability to have both real-time communication and real-time command control capability within the single device. We also focused in terms of security. This device actually has its own dedicated GPU for graphics and for being able to drive a GUI. And we also looked at, from areas of functional safety, those R5s could actually be run in lockstep or separated. So you now have, combined with the programmable logic, you now have a very high fault-tolerant capability for functional safety type applications, very critical in industrial systems.
Sure.
And we also had a dedicated security engine and dedicated power management Obviously, with all these different processing engines, we want to have the ability to very tightly control the power. Through the power management engine, we can actually control on a core-by-core basis and on a feature-by-feature function. And as you can see from the example here, you can see the areas in sort of a natural partitioning between application, where you would have your guest OSs running, your hypervisor, and your real-time with the dedicated RTOS, or even bare metal, and the safety and security functionality, the graphics processing. And then within the programmable logic, you can see areas for being able to accelerate, using that to accelerate the algorithms running on the processor, to do dedicated motor and motion control, as well as the sensor fusion, the real-time analytics, even machine learning for neural networks, being able to tie that in with the programmable logic and extension of peripherals, as we talked about earlier. And then you also see the connectivity. So we've extended in terms of the types of peripherals as part of the processing unit, and we're going from USB 2.0 to USB 3, adding PCI Express natively to the processing system, also offered as hard blocks within the device itself. But a lot of capability, a lot of configurability, again, multi-layer security, multi-level safety, very well suited ideally for industrial IoT applications. And just some examples of where we see that with the whole Zynq programmable SoC family, giving you quite a bit of scalability for moving from a low-end application to a mid to a high-end application. And you can see a variety of different application spaces, whether it's robotics, whether it's transportation type applications, surveillance, smart grid, and even medical, and then of course with smart manufacturing.
Okay, Dan, so I've heard about this fourth industrial revolution going on and how the Internet of Things is bringing on some seriously big-time change. Can we talk about that a bit?
Yeah, if you think about it, we're really moving and transitioning from the third generation, our third industrial revolution, where it was really about the automation. Even stepping back from that, you look at it from the very beginning where the industrial revolution started, where we actually had the automation, mechanical automation, and steam engine really ushering in that initial industrial revolution. Then moving up and bringing in the ability to have the full industrialization, where you have the assembly line tying in, and then moving into the third generation where we have now more of the electronics and the computers involved in that, and that was in the mid-50s. But now really looking at the fourth generation, or the fourth revolution as it's termed, is bringing in these cyber-physical systems. Now you're bringing in the combination of the physical, the operational side, some people call that the OT, and marrying that with the information technologies, with the Internet of Things, so they call that the IT. So you're seeing this convergence in this fourth industrial revolution of the operational with the informational technologies. The OT converging with the IT, really bringing this smart automation capability. And there's actually a big initiative started over in Germany, which is called Industry 4.0 platform. And that's really to how can this new fourth revolution be leveraged to optimize and bring more efficiencies and capabilities in terms of the manufacturing. And there's a big focus on this in Germany.
All right, Dan, can you give me an example of where you see the cloud acting as a disruptive force?
Yeah, I think if you look at it in terms of where the manufacturing is today, the bulk of that, you look at it viewed from a hierarchical scenario where you have the command and control going down from the top from your enterprise resource planning all the way through the SCADA systems into the PLC and to the actual things, and then the information coming back up. So very hierarchical in nature. And as the slide is showing you, moving towards the future is the cloud functionality is really coming down into those different levels and displacing the ERP, displacing even at the SCADA level, and more of a peer-to-peer or machines-to-machines scenario as opposed to this hierarchical structure that exists today. You can see some of these examples. In fact, there's a great example of how a water filtration plant was looking to upgrade their systems, and rather than rip out all the systems they had and go through and buy new equipment, they were able to leverage the cloud services.
Nice.
And the cloud services were able to provide a lot of that similar functionality much quicker and more cost effective.
Okay, Dan, so we heard about the programmable SoCs and the advantages those bring, but how is that represented in a factory environment where all of this industrial 4.0 business is going on?
That's an excellent question. And again, from what we saw earlier, where we have this hierarchical approach giving way to more of a peer-to-peer machine, even all the way from edge to cloud,
Yeah.
the programmable SoCs really fit in nicely because they can actually tie in all of these different aspects. Where I talked about the real-time command control, there you can see how they could be tied directly into the motor control, the motion control, while at the same time, there's the visualization aspect through the HMI, and then up into even with the gateway and being able to take all the sensor data coming through, whether that's coming directly from the source or through the gateway out up into the cloud to do those types of analytics, those less time critical things. Our devices are very well suited for that. In fact, through some of the use cases you're about to see, you'll see examples of each one of these areas and sort of the partitioning of the functionality that's key to realize this smart connected control.
Very cool. All right, so let's jump into some use cases.
Yeah, so one of these use cases you can see here, this is with the ZYNC programmable SoC. You can see the dual Cortex A9, the dedicated processing system. You can see the link from the communication side, from the peripherals themselves, again, supporting the industry standards and the protocol, communication standards and the protocols. If we look at the programmable logic, you can actually see the different types of sensors, where now you would have that sensor fusion taking place, almost in a way combining all that to create a virtual sensor, where now you have more information about the system, and then being able to accelerate some of the algorithms that might have been running on the processor, accelerate those through the programmable logic as dedicated co-processing engines, and being able to do in real-time analytics on that streaming data that's coming in through the sensors, and then even to have that visual display with the HMI and being able to have that displayed in this case. And that real-time analytics, again, being complemented off through applications or algorithms, things would be running in the cloud. So this sort of gives you a fully integrated PLC controller with HMI capability. And another good example would be looking at it from an intelligent gateway perspective. And again, from edge to cloud, so we're talking about the sensor fusion you see here. You can see the precision timestamping capability here implemented within the programmable logic. Another area is having this high reliability IP, and this is the HSR PRP, high reliability parallel redundant protocol. So having dedicated functions within the programmable logic that you wouldn't be able to see implemented in other off-the-shelf devices. And then the last use case is representative of even greater partitioning and functionality is with the ZYNC UltraScale MPSoC. Here you see the partitioning, as we had talked about earlier, of the cores themselves, both the application and the real-time, and then being able to have that high I/O bandwidth between the processing system and the programmable logic, and being able to implement things like that high fault-tolerant area for functional safety, different Ethernet standards, the new evolving time-sensitive network TSN IP, and being able to have even more sophisticated control and capabilities through the higher performance fabric and higher performance I/O.
Okay, so Dan, we have a device and that's all fine and good, but what kind of ecosystem do you have to support us as engineers in this space?
Yeah, developers have quite a bit from that standpoint. We have a very extensive ecosystem where we're looking at it from a design enablement with a variety of different platforms, tools, kits. You can see modules and boards here, a whole variety depending on what you want that scales from the low end all the way up to the high end.
Nice.
Both ZYNC and ZYNC programmable SoC, a full complement of design service capability depending on what region in the world you are and what type of specialized functionality you would want. And you can see quite a bit of that in the upper box here, partitioning out depending on whether the OS that you're looking for, whether it's security focused, whether it's connectivity focused, whether it's safety focused. So it's a very, very extensive ecosystem. To be able to support that, if you look at the very top of the slide, that pipeline, where you're talking about sensing the information, bringing that in, being able to do the command control, process all that information, run those real-time analytics, and then connect and complement all that with functionality up in the cloud. So if we look at the design enablement a little bit more closely in detail, we have model-based design using MATLAB and Simulink to speed the development from both a hardware-software co-design capability, looking at the different toolboxes that MathWorks provides, also through the LabVIEW, being able to provide a industrial control, machine vision type functionality to target directly different types of algorithms to the devices. Their Compact Rio platform is really based on the ZYNC architecture, so it provides you that reconfigurable I/O, that compact in a variety of different levels of platforms. And then to be able to take your algorithms at a C, C++ level and be able to go directly implement them into the FPGA and really work at a much higher level of abstraction, and that's with our SDSoC environment. And then that leads right into not just the environments, but actually the kits themselves that are supported through here, and Avnet providing a industrial IoT starter kit. And this is based on the ZYNC programmable SoC. They have it both for the ZYNC 7000 systems or the dual Cortex A9, and they just recently announced Ultra Z, which is about the ZYNC UltraScale SoC, and that's a starter kit for development there. So being able to actually go ahead and implement using a variety of different types of sensors and do analytics and also have those real-time analytics, but also being able to have that direct cloud connectivity. In the example of the Avnet IoT starter kit, bringing that all the way up and working directly with IBM Watson.
Okay, Dan, I think I got the kit side of the story covered, but what about the different kinds of reference designs you've got?
Yeah, looking at industrial IoT and reference designs that would be important, there's actually quite a bit of connectivity reference designs that we have. You can see a couple of these different areas where you can take in the different types of industrial Ethernet standards and use the AnyBus from our partner HMS there. You can see Profinet, EtherCAT, PowerLink, a variety of these on the connectivity side. And then also from the standpoint of machine vision, embedded vision, reference designs, motor control. If you look at it again from industrial IoT, you're talking about the connectivity, you're talking about the security, you're talking about motion and motor control. So a wide variety of reference designs to address the different needs of industrial IoT applications.
Okay, so we've got kits, reference designs, but what's the development story here?
Yeah, and as we had just touched on briefly, using the SDSoC environment, you're really looking at being able to do both software-defined programming, you're able to do profiling at a system level, and it's not just about that. It's really abstracting your development to the level of C, C++, for your software developers to then be able to take those and implement those directly into the FPGA using this SDSoC environment. Again, you can profile the different algorithms, you can find the most computationally intensive, and then be able, using SDSoC, to be able to accelerate those algorithms and implement them. The other nice thing about what SDSoC does is it actually puts all the plumbing, so to speak. So it puts all the data movers, the data engines in place. So you don't have to worry about what do I need to do to interface between the processing system and the programmable logic. How do I ensure that I can have the optimal performance? All the data movers, that's all implemented directly through the SDSoC and automated for you.
So, Dan, how does this differ from, say, a traditional embedded software architecture?
Really, you look at what the industrial Internet of Things is adding is really being able to provide that layer of security, to provide the analytics, the real-time analytics. The slide is showing you here, you can see those differences in terms of the capabilities, having the virtualization with the hypervisor, the secure boot capability, so those different layers of security, and even within the hypervisor itself, through different partners, there's a way to have secure hypervisor, secure Linux environments. There's these different areas that IoT adds over a traditional architecture, and our ZYNC programmable SoC is very well suited to address those additional needs.
Okay, so how exactly does security fit into this picture?
Now, that's a great question. I mean, again, as we've talked about, the industrial IoT really brings a very strong focus of security. In fact, that's one of the top concerns when you go and talk to these manufacturers is about, I don't want to let my data out. I'm very concerned about being hacked or exposing that. And even worse than that, we're not talking about just losing some data now. We're talking about having irreparable damage in a manufacturing facility or other industrial type application. So where we fit, if you think about it, there's three real key tenets we look at, and that's anti-tamper, that's information assurance, and it's trust. And in fact, even within the Industrial Internet Consortium, they have released a document called the Industrial Internet Security Framework. The key theme throughout that is trustworthiness. And our devices, again, as I said, because we have that multi-layer capability, not just the hardware, not just the software, but also the flexibility through the programmable logic, we have that as our security monitored IP. So you now have 3 levels of security that you wouldn't have had in the past. From a hardware perspective, as the slide is showing you, we've got the encryption, we've got the authentication. We even have onboard A to Ds where we're monitoring temperature and voltage. We have a way to essentially brick wall the areas through our isolation design flow. At the software level, we have secure boot, we have measured boot, and that's actually part of the industrial IoT starter kit, and we've been able to show that. There's a great reference design exemplifying that. There's the trust zone, as you see from the isolation, as well as with the secure hypervisor to be able to isolate the different guest OSs and ensure that there's no corruption of the different areas or overlap. And then the runtime security IP also from our extensive ecosystem, and as I had mentioned within the programmable logic, different capabilities from a secure IP standpoint. So overall, 3 very strong layers addressing those 3 key tenets.
Okay, so what kind of tools and platforms are we really talking about here?
For developing the FPGA, we have our Vivado development environment design suite. And that includes our HLS, so the ability to do the high-level synthesis, take those algorithms, implement those in the FPGA. We have the software development environments, what we call our SDX environments. These are familiar environments that your software developer will recognize right away. They're Eclipse-based, again, providing you that automation of being able to take your algorithms and then implement those directly into the FPGA without writing RTL or it being at the low level. It really abstracts that up to the level of implementation for ease of use and ease of implementation. It's also to be able to rapidly iterate and try different algorithms and be able to profile those again and accelerate where you need to optimize your design to meet the requirements. So from a quick, rapid prototyping of the partitioning of your system to be able to address the requirements, SDX environments provide that. And then as we had talked about before, looking about the extensive ecosystem that we have that covers all the areas from the design enablement, the IP, the additional environments, whether it was through MATLAB, whether it was through LabVIEW or other areas to accelerate your design. And even with the boards and the kits and the platforms being supported by the various development environments to help to rapidly enable you to get your design to market.
All right, so Dan, tell me about the scalability story here. Can I go from low to mid to high?
Yeah, that's a great question because if you look at it, especially within our programmable SoC, as the slide is showing you, you have a variety of functionality, not just even the programmable SoC, but across our entire all programmable technology families. You can see here from the different types with the Spartan class or Arctic class, which is the base FPGA, but then you add in the programmable SoC, and even within the latest one, you get up to 21 different types of devices in terms of footprint migratability and features and functions. Getting back to that point of the right engines for the right tasks. These have both the graphics, they have video codecs. So we have these tremendous number of devices that can be scaled for meeting a low to a mid to a high-end application. And even we have a single core for the more cost-optimized solutions. We have a single core A9 processing system. Again, all the advantages that the Zynq programmable SoC brings, but with just one single ARM A9 system to give you that full capability. So you scale from a single core all the way up to quad core. You scale on performance, you scale on capability, on I/O, a wide breadth to meet the variety of different types of applications that you see within the industrial IoT.
Okay, great. So Dan, can you recap your main points for me?
Yeah, so I think if we look at it, again, having a platform that's scalable, having a platform where you can do the real-time processing, the application processing to meet a variety of different types of connectivity, standards, and protocols, to being able to have a very flexible, highly configurable platform in terms of both the hardware functionality and the software functionality, and having the extensive ecosystem to be able to rapidly develop and accelerate your design, both with our in-house tools, through our Vivado tool suite, through our SDX environments, as well as with our extensive ecosystem. You can see how the Zynq and the Zynq UltraScale Plus MPSoC families are very well suited to meet the needs of the industrial IoT.
Excellent. Well, I think that's all I have time for today. Thank you so much for joining me, Dan.
Thank you very much. It's been a pleasure talking with you, Amelia.
And before we go, you didn't forget to click that link, did you? There you can find out more information about industrial Internet of Things solutions from Xilinx. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, head on over to YouTube, keyword eejournal, or check out the on-demand section of eejournal.com.